So I'm going to respond to Piazza Post 310 by Casey. So what's the difference between a uniform and normal distribution? And what is a normal? What is a uniform? And what's the difference? So first off, these are different distributions. We talked about in class the central limit theorem, which says that if you average enough independent, identically distributed random variables, then you converge to the normal distribution for a large enough average. That's a separate case. So you can say if you average a bunch of uniform distributions that these are independent distributions, separate distributions, but identically distributed, then you converge to the normal. But the uniform is still different from the normal. So if you average a bunch of them, you converge to normal, but uniform distribution is different from normal distribution. So I'll talk about what these are. So what is a uniform distribution? So there are two types of uniform distributions. There is the discrete uniform distribution. And you can describe this nicely using a PMF, probability mass function, right? So discrete uniform distribution is probably what you think of when you think of a uniform distribution. So the probability of taking on any of a finite or countably many number of values is given by, is the same. So let's say in this case, the probability would have to be 1/4 for each of these possible outcomes of the random variable, right? So the range of the random variable x, let's call this is the random variable x, this is the distribution of the random variable x, the range of x, let's say is equal to 1, 2, 3, right? So you could say that, or the probability of x taking on any other value is also 0. So you can look at it a few different ways. But anyway, so it takes on values in this. It takes on these values with equal probability. So compare that to the continuous uniform so this is the continuous uniform distribution. You can draw this nicely using a PDF. So you have PMF, PDF, and CDF, right? So we'll draw the CDFs after. But if you want to draw continuous distributions, you want to draw them using PDFs or CDFs. If you're drawing discrete distributions, you want to draw them using PMFs or CDFs. So CDFs can draw anything. PDFs draw continuous distributions nicely, and PMFs draw discrete distributions nicely. So here, this is the density. Let's say this is the interval 1 to 5. So the density on this interval must be 1/4. So what does this mean? This means the probability. Let's say this is an interval. Let's say this is an interval from 2 to 3, right? Let's say this is the width of this interval is 1, and this is the interval from 2 to 3. So the probability of being in this interval between 2 and 3 is 1/4. So it's the density times the width. The density is 1/4, the width is 1, so the probability is 1/4. So this is a uniform distribution. So this means that the density at each location is the same. So over here, the probability of being at each location is the same. Here, the density is. So the probability of being at any particular location is 0. You can't talk about that probability because it's continuous, so there are uncountably many values here. So you can't have a finite probability of being at any particular location, or the sum of all these probabilities would be infinite. But if you take any interval, take an interval of the same size, so let's say this is an interval of width 1, and you just move it around. The probability of being in this interval, no matter where it is, between 1 and 5, is going to be 1/4. So that's what it means to be uniform. The density at each location is the same. So if you take some interval of any size and you move it around, the probability mass in that interval, so the probability of a sample landing in that interval, is the same no matter where it's located. So let's compare this to a normal distribution, right? So a normal distribution, a normal density looks like this. Okay. So normal density looks like this, and this is a PEDF, right? So a density function. So if we want to draw, if we want to make the comparison here, take an interval. Let's say this is between 1 and 5, just like this uniform. Take an interval of width 1, and take this other interval of width 1, right? So it's pretty clear that the mass here is smaller than the mass here, right? So the mass is just the area under the curve in that region. You can think of it as an analogy to physics, where the mass is the integral over volume or length or width, volume, length, or area, or some other dimension of the density function. So mass is the integral of density, or density is mass divided by length, or mass divided by volume. You can reverse that. So here, the mass for this region is larger than the mass for this region. So let's say this is probability, I don't know, making something out, 0.5. This is probability 0.3. In this case, the probability for this interval of width 1, no matter where it is the same. So these are clearly different. I mean, just looking at the diagrams, they're different, right? You can get some properties that relate these, but they're different. They're very, very different. Another thing to describe these, you could describe them using the CDFs. So here the CDF would look like this, 1, 5. As you go along, as you move along this interval, you're accumulating the same amount of mass per unit length at each point. So if you jump a little bit here and you jump a little bit here, you're accumulating the same amount of mass. So the slope is constant in this interval. So that's why the CDF for a uniform distribution is a straight line, because for each interval in the PDF, you're accumulating the same amount of mass. So it just goes up linearly. Another way of thinking about it is the derivative of this is this. The derivative of a linear function is a constant. And the integral of a constant is a linear function, right? So linear, this is the derivative, this is the integral of this guy, right? This guy over here, it's actually not continuous, and it's not differentiable. So 1, 2, 3, 4. So this is 1, this is 5. So this guy, this is the CDF. The CDF corresponding to this PMF. So at each point, at 1, it jumps up infinitely fast. So it goes, the mass you've accumulated so far is nothing, 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 and then all of a sudden we accumulate a quarter probability mass, right? We accumulate this all in this little tiny area, of this little tiny length here. So we jump up by 1/4, and then we continue. We jump up by another quarter. We continue. We jump up by another quarter, et cetera, et cetera. Right? So that's what the CDF for this looks like. So if you try to differentiate this, it's not even continuous. So you can't. There's no way you can. It's definitely not differentiable. You cannot differentiate this. So you cannot map this to a PDF. So always use a PMF to describe a discrete distribution, and use a PDF to describe a uniform distribution. A continuous distribution. Uniform, you can describe, depending on what kind of uniform, you can describe it using one of these. So continuous, use a PDF. Discrete, use a PMF. And then the normal CDF, you've probably seen this, looks like this, right? Again, totally different from these guys. This is definitely not linear. This is like a sigmoid function. It goes up like a logistic function. So this is, if you notice, the slope here corresponds to how much mass you're getting per unit length here. So at this point, let's say this is 1. Per unit length, there's very little mass that we're getting. As we move along, we're accumulating very little because the density at this point is small. So here we're accumulating little. The slope is maximal here. This is the highest. This is the greatest slope in this interval, right? Let's say between 1 and 5. This is the greatest slope, and this corresponds to the peak of this distribution. So at the peak, per unit length that you're moving along, you're accumulating the most mass. And then when you get back down to 5, the slope tapers off again. So this is the CDF for this normal distribution. So I guess those are some of the main characteristics of these distributions. There are other differences you can talk about, but I hope that answers your question.